Hello there. So let's turn to chapter 2 and take a look at subatomic particles for this week, beginning August 24th. So let's see where we left off with chapter 1. And we had been talking about these elements which were made up of very particular kind of atoms. And the atoms of one element were different from the atoms of other elements. And that's something that we're now going to look at in some detail, the makeup of the atoms that makes them similar or dissimilar to other elements. And it's based on the shape of the periodic table, because the periodic table shape is based on chemical reactivity. And that reactivity is based on the subatomic particles, where we find them and how many of them there are in each kind of atom for each element. So we've already looked at the periodic table, and we said through boron on the right hand block, the top left corner of that right block. Let me see. Where's my drawing tools? There we go. Of course, this is boron. And here, and then down this green diagonal, that gave us the majority of metalloids. And to the right, we had non-metals, also including hydrogen. And then everything else, well, we've of course got germanium and antimony to also include for our metalloids, but everything else is a metal. And so we had started to put names to these groups of elements. First group we want to look at is the noble gases, which are all similar to each other by their lack of reactivity. Every row, what we sometimes call a period, every row finishes with an element which is unreactive. And we'll talk in this chapter about why that is and what's going on with those subatomic particles to make them so unreactive. So when we break down an atom, we find three basic kinds of subatomic particle: protons, electrons, and neutrons. Protons are positively charged and live in the nucleus. The neutrons are neutral and also live in the nucleus, while the electrons live outside the nucleus in layers that we sometimes refer to as shells. Those electrons are negatively charged. So positively charged protons are attracted to negatively charged electrons, just as electrons are attracted to protons. That's one of the basic laws of chemistry. Opposites attract. But positively charged things are repelled by other positively charged things, and negatively charged things are repelled by other negatively charged things. The protons have mass like the neutrons, so all the mass of the atom is actually tied up in the nucleus, and the electrons are virtually weightless. That's not entirely true. There is a tiny amount of mass associated with electrons, but it's 4 orders of magnitude smaller than even the tiny mass associated with protons and neutrons, that we consider the electron to be virtually weightless. So close to zero, there's not really any worth in arguing about it. So these are our atomic mass units, AMU. This is just an arbitrary scale. So we compare an atom of magnesium, given us 24 AMU. We can say that an atom of titanium at 48 is twice as heavy. We'll get into actual mass measurements by gravity when we hit chapter 5. So the nucleus, like the nucleus of a cell, that's where all the mass of the atom is, with protons and neutrons. and then circulating like satellites in space around that nucleus are the electrons, locked in place because of their attraction for protons in the nucleus and also their repulsion for neighboring electrons that keep them in place. When we look at each element, we can sometimes list information about the element and its atoms next to its chemical symbols. And the primary piece of information we might talk about is the mass number, that count of protons and neutrons. And that mass number count is normally written in the top right-hand corner of the chemical symbol. So 14 for nitrogen, 16 for oxygen, and 24 for magnesium. Remember that mass number is protons and neutrons. Now in the bottom left-hand corner is where we normally leave the atomic number of the element. The atomic number is purely the number of protons, because that's the most distinctive piece of information about atoms for each element. No two elements have the same number of protons in a nucleus. So that is the distinctive piece of most distinctive piece of information that we have for atoms and their elements. Only atoms of nitrogen have 7 protons. Only atoms of oxygen have 8 protons. And only atoms of magnesium have 12 protons, I beg your pardon. The mass might be the same as the mass for other elements, but they're not going to have the same number of protons. That is absolutely unique for the atoms of an element. Now, we don't directly infer the number of electrons when we look at the chemical symbol normally, but we can work it out because we only have neutral atoms when there's an equal number of protons and electrons. For every positive charge, it needs to be cancelled by the negative charge of an electron for an atom to be neutral. If there was electrical charge in the atom, we should make it an ion. That's a chapter 3 chemistry next week. If there was an electrical charge, that would be written in the top right-hand corner. If there's no charge, we just leave it blank, and that only happens when there's parity between protons and electrons. Just the pure math of it. 7 positively charged protons minus 7 negatively charged electrons, 0 charge in the atom overall. So for this week, as we look at our examples which are electrically neutral, we can say because the atomic number of nitrogen is 7, which is the number of protons, because it's neutral, that's also the number of electrons for now. Finally, the number of neutrons, which also have mass in the nucleus, that would be the mass number, which contains protons and neutrons, subtracting the atomic number, the number of protons, and so the difference between the two is the number of neutrons. So we can normally allude to protons, neutrons, and electrons just by looking at the mass number and the atomic number. Let's look at an example. So 4 elements listed here. What would be the atomic number, mass number, and the proton, electron, and neutron count? Feel free to pause the video and fill in the answers for yourself. It's good to practice, and then we'll go over the answers in a minute. Okay, we're officially back. So for the atomic number, each time, that's the smaller of the two numbers. So that's 9, 12, 4, and 18. Because that atomic number is just a number of protons. So we can fill that in as well. 9, 12, 4, and 18. And with the atom being electrically neutral, because there's no charge shown, if there's charge, you have to show that in the chemical symbol. That infers that there's also 9, 12, 4, and 18 electrons. Mass number is the larger of the two numbers each time. So 19, 24, 9, and 40. And finally, the mass number, subtract the atomic number of protons. That gives us the number of neutrons. So 10, 12, 5, and 22. Protons and neutrons have the mass, and they are found in the nucleus. The protons are positively charged, the electrons are negatively charged. Positively charged particles repel other positively charged particles, but they attract negatively charged particles. Okay, let's move on. So although the atomic number is distinctive and unique for atoms of each element, the number of electrons is not, and we'll talk about that next week as we talk about ions when there is a charge, and also the number of neutrons isn't unique for atoms of an element. The number of neutrons can vary. And this gives us what we call isotopes for that element. Atoms of the same element, which have the same number of protons, but a different number of neutrons, and therefore have a different mass number. A majority of elements in the periodic table contain isotopes, some of them as many as 6 or 7. Remember, it's a different number of neutrons. So as we look at our example here, nitrogen 14 with 7 neutrons, that's fine. However, atomic number 6, that's not nitrogen. That's carbon, a completely different element. Atomic number 8, that's not nitrogen. That's oxygen, a completely different element. Nitrogen 17, having the correct number of protons, nitrogen 17 are atoms of nitrogen with 10 neutrons compared to its sister isotope with just 7 neutrons. When we look at these elements, it would be a pain in the butt if we had to perform calculations multiple times over because of multiple isotopes. So we take an average for the mass of each element based on the isotopes it has and the relative abundance of those isotopes. So for example, to be chlorine, it has to be 17 protons. But some of these atoms of chlorine have 18 neutrons, but some of them have 20 neutrons. So we work out an average, of course being neutral, that'd be 17 electrons. So we work out an average based on the relative abundance. That's one of the great things about the elements in the universe. You find a sample of chlorine in America and a sample of chlorine in, say, Japan. The composition, the makeup of the 35 isotope and the 37 isotope is exactly the same. So roughly for every 100 atoms, 75 of them will be the mass 35, and about 25% will be the mass 37. Always see consistent composition amongst the isotopes that make up that element. So we'll take just over 75% of the 35 mass, just under 25% of the 37 mass, and we come up with that abundance average of 35.45. The average weighted towards the most commonly seen isotope. And those values are the values that we see on a periodic table. We can take a quick look. I have to find my periodic table. There we go. So if you look at these elements, you see that many of these elements have a decimal place in their mass, and the existence of that decimal place suggests multiple isotopes. If there was only one kind of atom, then it would be an exact whole number. So you can see the vast majority of elements indeed have multiple isotopes. So we can use this idea of abundance average mass to calculate the average that we're going to take. Take this example here, the supposed new element which has been found. 30% of this new element has a mass of 280. 50% has a mass of 330, 125 being the atomic number for this new element, and 20% has a mass of 345. So we take 30% of the 280 by taking the 280 times 30 over 100, or by multiplying by 0.3, which is what we get when 30 is divided by 100. The 330 multiplied by 50 over 100, or multiplied by 0.5 because it's 50%. And the 345 multiplied by 20 over 100, or multiplied by 0.2. And added together, we get an atomic mass of 318 as an average. Importantly, it's heavier than the lightest isotope, but lighter than the heaviest isotope. So it is a true average, like taking the average height of people in the room. It doesn't mean that we have any atoms or any people who are that height or that weight, but it's got to be within the range. If your shortest person in the room was 5'2" and the tallest was 5'9", the average couldn't possibly come out as 6'3". So make sure that average you calculate is within the realms of possibility for the example isotope shown. Again, example you could maybe try at home. A different element which has 4 isotopes. What would be the abundance average mass? And feel free to take a second to try this for yourself. Okay, so let's look at this one. We want 18% of the 301 mass. So the 301 times 0.18, and that'll come out as 54.18. Added to that, we'll take 36% of the 323, which comes out as 116.28, and we'll take 9% of the 335 times by 0.09. That comes out as 30.15. And finally, if I can squeeze it in, 37% of the 338. And that comes to 125.06. So our grand total will be 325.67. Don't forget your units. That's AMU, atomic mass units. Most people find that fairly straightforward after a couple of examples. So let's see. Because isotopes are often used in medicine. because some isotopes are radioactive and emit radiation. Sometimes that radiation can be used to treat a patient with something like cancer, and sometimes used to actually detect cancer in a patient. We certainly see that with something like iodine, which is normally stored in the body, stored in the thyroid glands in your neck, and the thyroid glands use that iodine that's stored to produce the hormone thyroxine. Here's a picture of the thyroxine here. This is what we call a line angle formula, where we're just highlighting, for the most part, the chemical bonds between carbon atoms in the molecule. And so every time the line changes direction or changes thickness, that's the implied position of a carbon atom. And the majority of organic molecules are made up of carbon and hydrogen. Anytime there's a non-carbon, non-hydrogen atom in the molecule, we usually write the chemical symbol for that element. We sometimes show the hydrogen if it's part of a functional group or highlighting something like chirality at that point in the molecule. That's not something you really need to know for 141. I guess I'm just trying to be helpful, or maybe just showing off or something. Anyhow, so thyroxine produced by the thyroid glands. And if we think there's some medical concern going on with the thyroid, we can give a patient a radioactive sample of iodine. And as that iodine gets stored in the thyroid, it will emit radiation that can be detected by an imaging machine. And those images, by intensity of the radiation, show us where the iodine is being stored. If the two thyroid glands look to be the same shape with the same color intensity, that even spread of iodine suggests that we've got healthy thyroid glands. However, if one of the thyroid glands looked misshapen compared to the other, or looked much darker with lower intensity, that could be a sign that there's no iodine being stored in that part of the gland. It could mean that there are problems. So if the intensity of color from one gland to the other was like this, that could suggest, that dark area could suggest that there are actually cancerous cells in the thyroid gland. Could be something else, but cancer could be one of the considerations for treatment. We'll talk more about radioactive isotopes when we get to the end of the semester and chapter 10. All right, let's see how we're doing. So I tried to think where I left off with 141 yesterday, because I think it's prudent to just keep the same pace as them. And that, I believe, is where we finished off. So lectures from this point will now normally appear on Monday, Wednesday, and Fridays. Monday lecture is probably going to be maybe about 9 o'clock, maybe 10 o'clock Monday evening. Wednesday lecture will still be at that 11 a.m. time because that's the time for the section 1 students. And then Friday, because I'm actually in class doing a lecture at 11 a.m., Fridays, that last online lecture, will be again about 9 to 10 o'clock at night. It's probably just going to be the only time in my day that I can fit things in because it's pretty busy. So Monday night, Wednesday mornings, Friday night, that's a new time for lectures. So I hope that helped, and I'll talk to everybody soon. Stay safe, wear a mask, wash your hands.